Just a quick heads up, today's homework is going to be from your textbook. Okay, and therefore you will not see any new document being uploaded in Google Classroom, just a heads up. Anybody have any questions from the homework from last week, from last session, I'm sorry? Okay, just give me a thumbs up if you actually tried to do the questions. Thank you, Lily. Chelsea? JD, thank you, JD. Sorry, thank you, Chelsea. And thank you, JD, Alina. Okay, so we'll wait for your responses, guys. So here's what we will be doing in today's class. We're moving on to the next chapter. Last chapter was on Newton's laws of motion. And now today's chapter is motion in 2 dimensions. So you know that when we start studying physics, we do the basics, right? We study everything in 1D because that's easy for us to understand. But in nature, things happen in 2D, 3D, right? 4D even. And so it only makes sense to extend our understanding of forces and all other vectors like velocity and acceleration in the realm of 2 dimensions. And so that's what this chapter is going to be all about. And so we're going to study what's called the head to tail method for vector addition, head to tail method for vector subtraction, and then we're going to take a look at some problems today. All right, so this is all in all a solid problem solving type session, but you will have to do that because if you don't do problems when you and I are together, it's going to be not a fruitful session. Okay, in the textbook, this topic over here, head to tail method, is called the graphical method. Okay, so just so as you know, when you're referring back to your textbook, it's called the graphical method. So whether you call the graphical method or the head to tail method, it is the same thing. And so even in vector subtraction, this is the graphical method. So when we do the problems, you will see we are also going to be talking about adding and subtracting vectors. There's another method, not just a graphical method. The other method is called the analytical method. So we're also going to be taking a look at that today. All right, as usual, folks, please let me know if there are any questions. Feel free to stop me and say, Ms. D, you need to stop and re-explain this. Okay, please feel free to do that. Also on the top over here, you will see the homework that is going to be assigned for this, this session. And so as I start teaching, feel free to take a picture of the homework over here and keep it handy. Make sure you do that homework, all right? So take a look at the scenario that is shown in this diagram. So you will see that this person over here is under the influence of 2 forces. She has 2 friends, one standing on her left, the other one standing behind her. And both these friends are pushing onto the main friend, number 3. Okay, now we'll see that friend 1 is pushing her to the right, and friend 2 is pushing her in sort of an upward direction. And so friend 3 is going to feel the effect of both those forces, F1 and F2. And here's where this session is different from what we did last time. Last time, we only talked about forces acting all along the x-axis or all along the y-axis. We did not analyze situations where there were forces along the x, which is kind of like the F1, and forces along the y-axis, which is the F2. All right. So from your background knowledge, right, if you were the person number 3 and you had 2 friends pushing you in those directions along F1 and Fy, think about it. In which direction would you actually feel the total force? right? And say this to yourself, which direction do you think I will be feeling the force? So there's a little bit to the right, little bit to the upward, that's the push. And so what you do is you combine the effect of both the forces. So a little bit to the right, that is this one right here, okay? And what you do is where you ended that arrow over here, at that point, you start drawing the second push, that is F2. And so you have a little bit of push in that direction as well by the second friend. So it's very, very, very important in the way these two arrows are drawn. So let me draw it out again over here. So you have F1 pointing to the right. And where you left off the F1 near the arrowhead, the red dot, from there you start drawing the second push. So the second push by friend 2 is going upwards like that. And so this is how you draw the two arrows. Okay, now this part of the vector is called the tail. And where you put the arrow is called the head of the vector. So what we did is, where you have the head of the first vector, that is F1, right from there, you start the tail of the second vector. And so that's why this method of drawing the vectors together is called head to tail method. It's called head to tail. So head of the first one attached with the tail of the second one. So this is how you would draw the vectors when you do vector addition. Okay. Now, by the way, what's vector addition? Well, now what that is you have two vectors and you're combining the effect of both those vectors to find out, well, what's my resultant effect? So basically here we're trying to find out what's the resultant push that student 3 is going to be feeling, right? So we need to find out the resultant push. And so once you draw the head to tail, then what's going to be your resultant vector? Well, you go from the tail of the first one to the head of the second one. So draw the resultant vector from the tail of the first one to the head of the second one. This becomes your resultant vector. Okay, and of course, because we're talking about vectors, we also need to give some idea about the direction. And so you will see in the solved problems that we will also be trying to determine that angle. Okay, and so when you try to find out the effect of two or more vectors to find out the final resultant, that process is called vector addition. Okay, and so you will see that the head to tail diagram is already drawn here. So this is the first one, F1. Okay, that's the first vector. From the head of the first vector, you draw the second vector. So you have what's called the head to tail arrangement. Okay, and then how do you find out the net? Well, you go from for the tail of the first one, you go to the head of the second one, and that's going to give us, that theta is going to give us the direction in which that net force or the total force is going to be felt by student 3. Okay, and so in reality, there are two methods of doing that. One is the graphical method, and the other one is the analytical method. The graphical method it involves a little bit of approximation. Okay, there's a little bit of approximation, and the analytical method is accurate. There is no approximation over here. Okay, so we are going to be putting more focus on the analytical method, not so much the graphical method, but you still need to know what the graphical method is. So we're still going to do it, but we'll be spending more time doing the analytical method. Okay, so right now we're only talking about vector addition. So we're working on this part of our plan for today, okay? So let's do a worked example to understand how do you add the vectors, how do you put them head to tail, how do you find out the resultant vector and its direction. I'm going to take a pause here just to make sure everybody is on board with this, guys. Any questions for me so far? Okay, just give me a quick thumbs up if we are ready to move on. Quick, let's do that. Thank you, Lily. All right, other folks hiding behind the camera, hopefully you guys are paying attention. Speak up if you have any questions, okay? All right, so let's take a look at this example over here. So use the graphical technique, here I'm reading right here, use the graphical technique for adding vectors to find the total displacement of a person who walks the following 3 paths. So you have one person who takes 3 different paths, and we're supposed to find out the net displacement, okay? So what are the 3 different paths? Well, first he walks 25 meters in a direction that's 49 degrees north of east. Okay, let's call that part A. So you will see in the diagram here, it's shown that's the 25 meters, right? So what you do in the graphical method is you decide a scale. You would say, well, this much of distance is going to be like my 5 meters. And so I need 5 of those distances because I need 25 meters, right? So you decide a scale. So here the scale was roughly like, okay, this long a distance is like 5 meters. And so you go 2, 3, 4, 5. And so that whole thing would roughly mean 25 meters. So that's what that is. And we are also given the direction. It says 49 degrees north of east. Now, I'm assuming you guys know what that means when I say north of east. So basically, you're going from east in which direction? North. By how many degrees? By 49 degrees. So from east, that's on the x-axis, you're going towards the north by 49 degrees. And that's why that angle theta A is 49 degrees. So this is his first displacement. Okay, the second displacement is 23 meters heading 15 degrees north of east. Okay, so now 23 meters is going to be a slightly smaller length of arrow as compared to the 25 in A, because 23 is less than 25. And again, that angle is 15 degrees. And similarly, you would draw the final one. The final one is where is it? It is 23 meters. No, this one right here. He turns and walks 32 meters in direction 68 degrees south of east, 68 degrees south of east. And so that's the angle south of east and 32 meters. And so that's going to have to be the longest arrow, right? So see now that's the approximation that you have to do. So that's 5, 10, 15, 20, 25, 30, and a little bit more for 32. All right, so these are the three vectors. Now, these are not drawn head to tail yet. You will see that all 3 vectors are actually drawn in their respective x and y axis, right? You now have to combine the 3 vectors, put them head to tail, kind of like in this diagram over here, okay? So like the first one is this one. So you maintain the length, maintain that angle of 49 degrees. Then what you do is at the arrowhead over here, you draw a mini x and y axis like it's drawn over there, this one right here, the mini x and y axis. So you use that x and y axis to draw your vector B. Now be very specific that vector B needs to be at 15 degrees with the x-axis. And so let me just make it a little bit bigger. This angle right here must be 15 degrees. Remember to follow the directions, okay? So this one is 25 meters over here. B is going to be 23 meters. And then the final one, you again draw a mini X and Y axis, and I will see that it is in the fourth quadrant. So it's below the east direction. And so this is your second vector, 23 meters. And then that angle, of course, has to be 68 degrees. And that is representing 32 meters, I think it was, yeah, 32 meters. So now what we did is we arranged the three vectors head to tail. Because look, this one, head of the first one connected to the tail of the next one. Same thing, head of the second one connected to the tail of the third one. And then now, how do you find out the resultant? Well, you go from the tail of the first one to the head of the last one. Okay, and now what you do is, if you were doing this on a graph paper, like physically doing it, you would take a ruler and you would draw the vector going from the tail of the first one to the head of the last one, and this becomes your D total. So total displacement. D total, you can call it D net or D resultant, whatever you want to call it, right? And then, of course, you have to find out that theta. And so how do you do this in the graphical method? Well, you would take a ruler and measure that distance, measure the length using a ruler. Okay. And then you would take a protractor to measure that angle. Use a protractor to measure the angle. So this is the graphical method of doing it. And like I said, it involves some amount of approximation. Okay. And so before we take a look at the much more accurate method, that is the analytical method, I also want to show you what does it mean by the vector subtraction process. So we're now moving on to the next topic here, head to tail for vector subtraction. Again, this is still the graphical method, but more than showing you the graphical method, I'm interested in showing you what is vector subtraction. Okay, so now let's take a look at all right. So we're talking about vector subtraction, but you can think about subtraction just like addition with a little bit of a change. Wait, what? How is subtraction a little bit like addition? Well, take a look at this. Let's say I ask you to do 8 minus 5. What do you think the answer to that is? Come on, it shouldn't take you 1.5 seconds for that. 8 minus 5. Anybody just shout out? Anybody?
3.
3, yes, of course, right? Thank you for answering. 8 minus 5 is 3. Now, this is subtraction. I'm subtracting 5 from 8. However, can I not write 8 minus 5 like this? 8, to that I add negative of 5. Wouldn't that also give me 3? Yes or no? Anybody? Wouldn't 8 added to negative 5 give you?
Yes.
Yes. And so what I did, that's what I mean, that look, this here looks like subtraction, and this here looks like addition. The only difference is you're not adding 8 and 5. If you want to change that to addition, you would add 8 to negative of 5. So whatever is the number that gets subtracted, you have to add the opposite of that number to the 8. right? You cannot do 8 plus 5. I'm not saying change 8 minus 5 and do 8 plus 5. And I'm not saying that's the same thing. I'm saying 8 plus opposite of negative 5. That needs to be added. Okay, so the same idea over here. You can do A. Now I'm changing the negative to a positive. And now what should I be adding to A? Any idea? Anybody want to take a guess?
Negative B.
You got that. Thank you for answering. So A, to that, you're going to add the negative vector of B. Well, what does that negative vector even mean? Okay, well, take a look. Let's say my vector A was in that direction. Okay, and vector B, let me draw it head to tail. This is, let's say this is my vector B. Okay, and I now have to do A plus negative of B. Oh, so first of all, let me figure out in what direction is going to be negative of B. So negative of B will be exactly in the opposite direction of B and same length. All right, say 1, 2, 3, 4, 5, same length, but in the opposite direction. And so that is negative of B. And so now I need to add A with negative of B. So these are my two vectors that I would add. And I've already drawn them head to tail. Look, head of A is connected to tail of negative B. And now I don't need the B here. I just drew it there. That would help me to find out negative B. And now how do I find out the resultant? Well, I go from tail of the first one to the head of the next one. So I'm ready to draw my resultant vector. Okay. That's my resultant or total. Okay. So this is how you would do vector subtraction. It's very similar to addition. It's just that you have to remember to figure out the opposite of the vector that gets subtracted. Now be really careful. You're not to find out the opposite of A. You are to find out the opposite of B. So whichever vector gets subtracted is the one you find out the opposite for. Okay, so let me give you an example. Let's say I had to do vector X minus vector Y. So you would find out the opposite of which one of these two vectors, X or Y?
Y.
Sorry, say that again, please. I couldn't get it. Y, you got it. Perfect, right? The rest of the process remains just like this. All right, so let's take a look at this example over here. A woman, this is where I'm reading, a woman sailing a boat at night following some directions to the dock. The instructions read to first sail 27 meters in a direction 66 degrees north of east. Okay, so let's just draw our X and Y. And we would say 27.5, and it's going 66 degrees north of east, right? So we have to decide some scale. So we'll just do the same one. We'll do 5, 10, 15, 20, 25, and a little bit. Of course, you would be using a ruler so it doesn't look this crooked. And then 66 degrees north of east. All right. So this is the first direction in which she needs to move. So 27.5 meters. Okay. Now, and then she had to travel 30 meters in a direction 112 degrees north of east, right? 112 degrees north of east. So her second one was to be this. So that's north, this is east. We need 112 degrees 112 degrees north of east, and how much? 30 meters. Okay, now 112 degrees north of east. So it's obviously going to be, if I call this space the first quadrant, that's the second quadrant. I hope you guys know what that is. Where's my vector going to be? In space 1 or space 2, given the fact that this angle is 90 and the angle in which she should be going was 112 starting from east. So if you start from east, when you get to north, how many degrees would you have covered?
90.
90, you got that. So 112 take away 90, how much was that? You still have to, you can stop here, right? Because the direction is 112. You have to keep going till 112. So from 0, you go this way, you're 90. And how much more would I need to go to make it a total of 112?
22.
22 degrees. All right. And so that's sort of the direction in which she should be going by 30 meters. Okay, so it's going to look like this. So 5, 10, 15, 20, 25, 30, roughly in that direction, which is the same as 22 degrees west of north. All right, so she had to do this. Okay, so let me draw my mini X and Y axis here. Okay, one sec. I'm just going to get rid of all of this. I need more space here. Okay, I'm going to draw a mini X and Y axis over here. And I'm sort of going to take, look, this vector B, I'm going to take it and translate it. Imagine you're picking up vector B and you're moving it so that the tail vector B is here. Okay, and so that vector B is somewhere over here. Do you agree with this? Just tell me yes or no. If somebody's talking, but I can't hear you. Are you muted as you're talking? Just a thumbs up. Ladies, we're good? Chelsea, Alina, JD. Are we good? Okay. Thank you. Just keep doing the thumbs up and ask so I know you guys are there, right? That I'm not talking in, just in vain. Okay, thank you. All right, so now you've arranged this head to tail, right? And so if you want to find out the resultant, you would go from the beginning of the first one to the end of the next one. Okay, let's continue to read. Okay, if the woman makes a mistake and travels in the opposite direction for the second leg, so the second leg, which is this one right here, she makes a mistake. By mistake, she goes in the exact opposite direction where she should be going. Okay, and now basically, where would she end up? Where will she end up? Excuse me. So the first leg over here is A. She does that properly, but the second leg, the vector B, she makes a mistake and she ends up going in the exact opposite direction. And so opposite of B, that's the negative of B. So I draw exactly opposite in that direction. Of course, it's got to be the same length, but in the opposite direction, right? And can you tell me if this angle over here is 22 degrees, then do we know any other angles? Let me just put A, B, C over here and D over here. Any angles that you would know if that one is 22 degrees? Would you know the angle between the A and the opposite vector? So that's the opposite vector negative B. Or would you know the angle between axis B and the negative of B? Which angle would you know if that one's 22? So it's kind of like this. You have this line, and you have, so that's your axis. And now you have like that, and that angle is 22. So would you know the star angle here, or would you know the dot angle here? Or would you know both? Okay, let me reword the question. Can anybody tell me the measure of that star angle?
22.
22, that's right. And so obviously if this is 22, then how much is the dotted angle?
68.
Sorry, how much?
68.
68, that's right. So you just do 90 minus 8. So this angle we know is 22 degrees, right? Okay, and so now what you would have to do is go from here to here. That's going to be your resultant or the displacement total. So you would measure with a ruler, actually you would find out the magnitude, whatever that is. You would take a protractor and measure that angle, and you would also give me the angle. So you would say, whatever that is, let's say that looks like 7 degrees. I'm just randomly giving you that. 7 degrees south of east. That's how you would then find out the total displacement. So where she would end up because of her mistake. Okay. If there are any questions, feel free to stop me. I'm just going to go back to our plan here and tell you we finished the head to tail for vector subtraction and vector addition. We also took, the example for that. Okay, and now we need to take a look at the analytical method, which is more accurate. So it's the same process. We still want to find out the resultant vector and its direction, but we're going to be doing it in slightly a different way. Okay, so let's take a look at this accelerating subway train example. Add the vector A to the vector B shown in the figure. Well, I'm going to draw the figure using the steps. So I'm going to explain the steps. The x-axis is along the east-west, right? So the east-west direction is our x-axis, and the north-south direction is where we're going to be drawing our y-axis, north and south. Okay, we also know that. Okay. Now, before we do this, let me just quickly ask you one question. Let's say I have my y-axis, I have my x-axis, okay? And now I have a vector that is a force vector, for example. And I also know this angle is 30 degrees and the force value is 20 newtons, okay? Now, have you guys, in kinematics, have you learned how to find out the components of a vector? Yes or no? If you're talking, just make sure you're not muted. Have you done vector components, as in to find out the x component of the given vector and the y component?
No.
You've not. Okay, so we are going to actually do that right now, okay? So you know that, let's say right at the origin is where a piece of a rock is placed, okay? And I am applying a force in that direction shown by the blue arrow. So obviously this stone is going to feel a little bit of pull in the x direction, right? Now remember, I'm still pulling along the blue vector, but because of that pull, there are going to be two different pulls. One, the stone is going to feel a pull in that direction, okay? And the stone is also going to feel a little bit of a pull in the upward direction like that. This is very similar to the first situation we analyzed. right? So I'm saying that the stone is actually feeling a force in that direction. Therefore, that force can be divided up into two parts. One is the rightward part, and the second one is the upward part. Okay, and so that's what we're doing over here. And so I'm interested in finding out, well, how big is the rightward pull? And that rightward pull is called the x part of the vector f. So vector f, x part, because it's along the x-axis. And the upward push is called the f and the y part of it. Okay, so if you pull the stone at 20 newtons, 30 degrees north of east, then what's going to be your x part and what's going to be your y part? How do I find that out? Well, it's going to be very easy because you've learned how to use trigonometry if you have a right triangle. Right? Now, I want you to understand here that your hypotenuse is along the blue vector. Okay, your adjacent side to the 30 degrees, your adjacent side is the fx over here. Have you guys learned this in maybe grade 9 or 10? Yes, no? Have you guys
We are
learned?
not in grade 9 or 10.
But you guys have done this, right?
Like what are you doing?
So basically what I'm asking is, have you guys learned how to name the three sides of a right triangle?
Yes.
Yes, okay. And so Fy over here is called the opposite side to the 30 degrees. So Fx is adjacent side, meaning it is close to the 30 degrees. Fy is opposite of 30 degrees. And the blue vector, that is F equals 20 newtons, that becomes the hypotenuse. So this is like you have a right triangle like that. Pardon my straight lines. This one is the hypotenuse. That's the longest side, opposite of 90 degrees. Okay. And if this angle is theta, the side that makes the angle theta is called the adjacent. And the third side that's exactly opposite of theta, well, it's called exactly that, opposite. Okay. Have you guys learned sine, cos, and tan functions?
No.
As in sine is equal to opposite over hypotenuse. Cosine is adjacent over hypotenuse. Have you done this?
No.
You have not. Opposite over adjacent. Oh, you haven't done trigonometry, folks? Have you guys done? It's a field of mathematics. You must have done this in your math course. It's called trigonometry. If you haven't done that, then we would definitely have to take a pause here and go over the trigonometry lesson and then come back to our session. Because, and then come back to our topic, because if you don't know sine, cos, and tan, there's no way you can do the analytical method. So I'm going to ask everybody to respond. JD and everybody else. Let's see who are the participants. I need to know how many of you need an overview, or actually it's not even an overview, a lesson in that basic trigonometry. Everybody please respond. Alina, and just put your thumbs up if you want me to go through that lesson. Chelsea. Okay. I'm just trying to see how many of you are actually saying yes, but I'm struggling to see that for some reason. Yeah, I see Anne's thumbs up, but that's about it. Lily, what about you? JD, Chelsea? Please put your hands up once again so I know how to use my time in this session, folks. Okay, so Chelsea puts a thumbs down. Okay, so maybe Chelsea knows how to do that. Okay, so I'm just going to go with the majority and I'm going to quickly teach you this because we definitely need to know. Okay, so now let's say you have a right triangle over this, and I'm assuming you guys have never heard of the function sine, cos, and tan. Okay.
I think most of us have heard of it. It's just like we never actually learned about it.
You've heard of it, but you've never learned about it. Okay. All right.
Yeah,
so
if like everything we need to know is like sine is opposite over hypotenuse and stuff, I think that would be okay if you just put it there.
okay, so that's okay. If that's going to work for you, that's fine. Okay, so what I suggest is if you haven't got a lesson on that you take a mini lesson on that on your own. Okay, you can possibly go to Khan Academy and help yourself with that. Okay, so if everybody's okay with that, I can move on over here. Okay, so that's the decision I'm making. All right, so basically remember that we need to find out the magnitude of the adjacent push or the xward push, fx. Okay, so then if I do, let's say, cosine of 30 degrees, that is equal to the adjacent side divided by the hypotenuse. Okay, and so now cosine of 30 is going to be the adjacent side, that is fx, which is what I'm interested in finding out. And the hypotenuse is going to be the actual vector magnitude, that's 20, because I'm pulling at 20 newtons force, that's my hypotenuse. And so if I rearrange this, fx is going to be equal to 20 cosine 30. Okay, so pull up your calculators, folks. Make sure your calculator is measuring angles in degrees. It should say D or DEG on your screen. You would do 20 multiplied by, press the cos button, COS, and then punch in 30 and equals. You will see that that value is 13.3205. I mean, 17.3205, and we typically carry forward 4 decimal places, not more and not less. Okay, so what that means is that if you pulled a piece of rock with 20 newtons at 30 degrees, the rightward push that the rock would feel, that rightward pull is going to be of roughly 17 newtons. Okay, and same way we can find out the upward push using the opposite side. For that, you do sine of 30. Now, sine of 30 is opposite over the hypotenuse. And so opposite, we have Fy over the hypotenuse is 20, and you have sine 30 over here. So rearranging this, you have Fy equals 20 sine 30 degrees. Okay. So again, go back to your calculators. You go to 20, then press the sine button, SIN, and punch in the 30 degrees. Remember, it should be in degrees, not radians or gradients, okay? So that is 10 newtons. So what this means is the rock's going to feel a 10 Newton push upwards and roughly 17 Newtons push to the right, okay? So this is what is called finding the components of the vector. And the components are Fx and Fy. These are called the components. Really, what components means is parts. So your force 20 newtons has 2 parts, X part and Y part, but technically they're called the components, okay? So we're gonna have to use this method of finding components of the vector for this situation. Now you have a person first walks 53 meters in a direction 20 north of east, okay? So now the good thing is here you don't need to find out the scale because we're not doing the graphical method, okay? So you just draw a vector, making sure that you're drawing it at 20 degrees north of east, right? So 53 meters. So that's my XY axis, 53 meters. You don't need to draw that to scale, just say that that is 53 meters. It's a rough sketch. And that angle needs to be 20 degrees north of east. Oh, that doesn't look like 20, but whatever, right? 20 degrees, that's it. And then now you have your second one. The person walks 34 meters, 63 north of east, 34, 63. Okay. So 34 degrees, 34 meters, and that is 63, I think it was. Yeah, 63 degrees north of east. So these are your two vectors, A and B, that you need to add. Okay, now in the component method, that's the analytical method, you don't even need to draw them head to tail. What you do is you just find out the X part of each one of these vectors. So the X part of vector A, and then Y part of vector A. So AX and AY. So go ahead and quickly get me those values by using the sine and the cosine function. Okay, I'm going to give you guys less than a minute to do that. So determine AX and AY. Okay, and then you have the answer. You can share that with me. To make sure that's the equation you're going to use. So you take the magnitude of the vector, that's 53, multiply with cosine of that angle over there. Keep the questions coming, guys. You guys are awfully quiet. But I can only hope you guys are doing the work.
I got 21.6 for the X.
21.6, 53 cos 20. That's correct. And like I said, we're going to carry forward 4 decimal places. So 6, 1, 2, 9, and that's meters. Okay. Now, eventually, we would also be needing the directions for that. So we're just going to get into the habit of doing that. Now, if your AX is pointing to the right, we're going to assign a negative. But let's say in some question, you have a vector that was in that direction, and you were trying to find out the X component. Then here, the X component will be pointing to the left. Then you would put a negative over there. Okay. But this is not the situation right now, but just a heads up. So in this case, AX is positive, so we leave it like that. What about AY? Well, AY is the opposite side, so you would use the sine. So you take the magnitude 53 times sine of 20 degrees. Somebody give me that value. So 53 sine 20. Anybody?
I 18.1271.
Perfect. 18.1271 meters, and it is going up, and so it's going to stay as positive. Okay, so what we found out is AX and AY for vector B. We're going to repeat the process for vector B, and this time we can be faster, folks, because it's the same method. Okay, so BX is going to be, take the magnitude of the vector cosine 63, and then by would be magnitude times sine 63. Okay. So bx, anybody?
I got 33.5205.
Are you doing 34 cos 63?
Yeah.
Do you want to do that again for me? Can I get a couple people to try that, please? So do 34 multiplied by cosine of 63. Anybody else can tell me that?
15.4357.
15.4357. Yeah, that sounds about right. So I don't know what was the mistake that you made first time. Just make sure you know what that is, okay? So you don't repeat it. Okay, and then on that same note, 34 times sine of 63 is going to be 30.2942. And both of those are in meters. They're positive because they're pointing to the right, and the other one's pointing upwards, okay? All right, okay, so what this means now really is that you found out the total motion along X and the total motion along the Y. And so if I were to combine these two, this is what's going to look like. So it's going to be my X, Y, and then my vector A in that direction, and then my mini X and Y over here, and I have my vector B in that direction. So I'm drawing this head to tail, okay, just to show you one thing, that is 20 degrees. This is vector B, and my resultant will go from this tail to that head over here. This is going to be my D total, okay? So now what I just did is, well, I found out the X part of vector A that brought me this far, and then X part of my vector B that brought me this far, okay? So along the X, totally the person moved this distance. So this one is AX, and from here to here is BX, okay? And now what I also have along the Y is this. Because of the motion along A, it moved this far up north, right? That's the Y component. I'm just drawing it on the Y axis. And then my B goes from here to here, so the Y part. So these two Y parts are over here. So here to here is the motion along Y due to A, and then from here to here is BY. So now what do you think? How would I find out the net motion, D net, along X? How do I do that? Any idea?
Add the x's.
Add the two X parts. Perfect. So you do AX plus BX. Both are to the right. So obviously you have to add. If one was to the left, then you would have to do AX minus BX. Okay. And then similarly here, because both these are pointing upwards, you add AY to the BY. Right? Okay. So let's just do that. So we're now ready to find out D net X, okay? So that is AX plus BX. AX over here, we found out was 21.6129 plus BX was 15.4351. Can somebody add those two and tell me how much that is?
37.048.
37 sorry, say that again.
048.
048, like that? Like that? Hello? Okay.
Yeah.
You can correct me if that's not that is. And D net Y. You're going to add AY plus BY together. AY was 18.1271 plus BY is 30.2942. Okay, can somebody add those two for me?
48.4213.
4213 meters. All right, perfect. So now what we have is this. We have the total along the X that is this one over here, 37.048. And then we have the total along the Y, and that is 48.4213. Okay, now remember that we're now ready to find out the total. And so for that, these two, the net X and the net Y vectors, need to be head to tail. And so that's why I have this green part. Okay, to that, from that arrow, I draw the blue part. That's the D net Y. And then obviously you would go for the D total, you would go from the tail of the first one to the head of the second one. So the pink one is your D total, right? Now you can use Pythagorean. So you can think of this as a right triangle, A, B, C. Have you guys done the Pythagorean theorem? Can I see a thumbs up if you have? Thank you, JD. A couple more people. Okay, so I'm just going to quickly show you how to use the Pythagorean theorem. Again, if you have not done a lesson on that, you can go to Khan Academy and...
Everybody said thumbs up.
Everybody said a thumbs up? Okay, well, I'm not able to see that. Anyways, all right, so then D net Y, or the D total. Oh, you know what? I called it two different names. That's not cool. Basically, that's the D net over here. So that's going to be the square root of your D net X squared plus D net Y squared. Okay, so put in those values and find out the D net Y for me. So 37.048 squared plus 48.4213 squared.
I got 60.9687.
9687. Okay, can I get one more person to confirm that, please? So that is your magnitude. Remember, it's still the magnitude. We still have to find out the direction. So we have to find out that pink angle over here. So how many degrees north of east is what we have to find out. Now, we can easily do that because look, we have the adjacent side value and we have the opposite side value. And so you can use the tan function. Okay, tan of theta. Let's call that unknown angle as the theta. Theta is equal to opposite over adjacent. Okay, so theta would be, what you do here is, see, you're bringing the tan over to this side. And so in trigonometry, we do tan inverse. I hope you guys have some idea about this. Otherwise, it's just going to feel like baseless. Okay, so what you would need to do is tan inverse. Now, opposite side is this one over here, opposite of the theta. So 48.4213. 48.4213, divide that by, the adjacent side is the net x. So 37.048. Okay, and so what you would do is, in your calculators, you would press the function or the shift button, one of the two, usually it's the top left. I have shift, and then you press the tan. So shift or function and then press tan. You will see tan inverse in your calculator screens, and open a bracket and then punch in those numbers, 48.4213. Divide that by the other number. And then close the bracket, enter. And somebody tell me what value they're getting.
$52.5798.
Perfect. 52.5798 degrees. And usually the degrees are approximated to the nearest degrees. And so we're going to use the even odd rule here to say that is 52. Some textbooks will give you 53 degrees. You can follow whatever your teacher's rule is. Usually if the drop number is 5 and the very next number is even, you leave it as 52. But if it is odd, then you bump it up. Okay, so either 53 or 52, that really depends on what you guys are doing in your other courses, like in chemistry. Have you guys learned the even odd rule?
No.
You have not. Okay, so in that case, we're just going to be, because this looks like it's more than 0.5, so we're going to say 53 degrees. Okay. All right, so now we have the complete answer for D net y. D net y. That is equal to, you would also round this to the appropriate accuracy. So let's take a look at the values that are given. Now, you guys did say you've done scientific notation. Have you, or am I, maybe it was some other class? Have you guys done significant digits? Sorry, not scientific notation. Significant digits? Yes or no?
Yes.
JD, are you saying something? Sorry, you're muted.
Yeah, I said yes.
Yes, okay, so that is 3 significant digits. That is 3. Oh, sorry, no, we're doing this question here. So anyways, that is also 3 degrees, 3 sig figs. These are all 3 significant figures. So obviously, your final answer should also have 3 significant digits. So round this so that this has 3 significant digits. How would you do that? 60.9687.
61.0.
You got that. 61.0. That's 3 sig figs meters. And you're now ready to give the direction in the square bracket. And we said that is 53 degrees north going from east. So start at east going towards north. So 53 degrees north of east. So that becomes the final answer.
Isn't it D net?
That is D net, yeah. Sorry, that is D net. You're right. Okay. So questions about this process. I'm going to take a quick pause here. Any questions? Okay. All right, so what we did here is, usually what I do is I do one more problem, but I guess you guys will, you guys got this. All right, so however, I am going to be assigning a lot of homework questions. So if you're struggling, then we can definitely address this next week. So it turns out we finished this part as well, the analytical method. That's the more accurate method. So what we can actually do is we can move on to the next topic. And that next topic, I think, was projectile motion, if I remember that correctly. So I have time to actually do that topic with you guys. All right. What I'm doing right now is just about making sure that is the next topic. There, yeah, projectile motion. And does that come right after what we are doing? Analytical method, yeah, that's right. So let's do an introduction to projectile motion, okay? Now, projectile motion is actually motion in 2 dimensions, okay? So let's say, take a look at this guy kicking the football at an angle, right? So obviously that football is going to go up, reach the highest point, and then come back down. And so its trajectory or its path is going to look something like this. Okay. So you have this person kicking the ball. Let's say the ball is originally placed at the origin over here. So X and Y, this is where the ball is placed. And the person, let's say, kicks the ball in that direction. Okay. Let's say he kicks it with an original speed of VI, and that angle is, let's say, also given. And this x-axis, basically the direction that is parallel to the ground, is also called the horizontal. Okay. So obviously you can see now that this ball is going to go up and then reach a maximum height and then come back down like that. So it's going to reach somewhere over here. Okay, so this distance over here from the start to finish, this distance is called dx, obviously because it's falling on the x-axis. It's also known as the range. So distance between A and B is the range. Now, remember that the ball is actually not traveling in that direction. No, that's not what the ball is doing. The ball is actually going along the parabola that is drawn, that goes up and then down. So that yellow path is what the ball is actually following. But in doing that, this is its final location, DF. Okay, at B, that's the final location, and at A is its initial location. So you will see that the final location is to the right of the initial location. So obviously the object has traveled by some amount horizontally. Okay. Now, as it goes from A to the top part C and then comes back to B, the object is also simultaneously representing some motion along the y-axis. So as it goes from A to C, vertically, it is going from A up until this point right here, vertically speaking. And then as it goes from C down to B, vertically, wouldn't you say that it comes back to where it started, which is at A? Just vertically speaking, yes or no? It starts at the level of A, reaches that level that corresponds to C, and then it comes back down to the ground level.
Yes.
All right. And so what you can say that the dy, the total displacement along the y in this case is 0, because it starts and ends at the same level. That's A. Okay. So the motion of this object, where it follows a parabola, the path that it is taking right now, the yellow path, the blue path even, is called a parabola, right? Any object that moves horizontally as well as vertically simultaneously under the effect of one force, the force that is acting on the the soccer ball, when it is in air, the only force acting on it is Fg. That is because when we start studying about projectile motion, you are going to neglect air resistance. Air resistance is neglected. And therefore, the only force acting on the ball is Fg. And so if you were to draw the FBD of this ball, this is what's going to look like. The only force acting on it is Fg. So the normal question that I get is, if the force acting on the ball is downward, why doesn't the ball just fall down like that to the ground? Why does the ball actually go up and then down, right? So the reason for that is, look, I am not kicking the ball vertically up. If I kicked the ball vertically up towards the sky, it's going to go up vertically and come back down vertically. That's because I did not give it any push along the horizontal. If I kicked it kind of like in situation 1. But in situation 2, look at the way in which I am kicking the ball along the second vector, vector 2. I'm kicking it at an angle. It's not strictly vertical. And so that original VI has 2 components. It has X component and it has a Y component. And so because of that X component of VI, that's VIX shown with the green, the ball is not just going to fall down vertically, it is going to go up and down, but it is also going to travel horizontally because of that horizontal component over there. And therefore, the horizontal and the vertical components happening simultaneously result in the path being a parabola, right? A parabola looks like this. It starts, goes up, and then comes back down. It has a maximum point that's called the vertex. Okay, now sometimes, in different situations, projectile motions, vertical displacement might be different. So for example, let's say I had this person So you will see that the ball did not start and end on the same ground level. Where is my final location? Well, right here is my final location. Where was the initial location? Well, look, it's here. So the final location of the ball is above the initial location. And so there is some net vertical displacement. You cannot say it is 0 because it didn't come back down to the same level. So whatever that height is, that becomes the dy. Okay, so let's say that height is 5 meters, it's going to be plus 5 meters. That's going to be the value of dy. In yet again another situation, let's say you kick the ball but then let's say there's sort of like a pit in the ground. So you kick the golf ball, it goes up and then lands down in the pit. Okay, here's where my DF is. Here where my DI was. Now you will see that the DF is below, vertically below DI by this much distance. And so let's say if that was 2 meters, then dy would be negative of 2 meters because df is below di. In the first case here, df was above di, so it was positive. Here it is negative. Okay, so this is what you would have to be careful about, the vertical displacements. Now about the different types of projectile motion, okay? 3 types of projectile motion. Let's say this time you're kicking an object from the top of a cliff. This dotted line that is parallel to the ground is called the horizontal. Okay. There are 3 ways of kicking it. One is when you kick up and to the right at some angle. Okay, so this is called a vertical launch. The second way of kicking it is you just kick straight along the horizontal. So this is just called the horizontal launch. And I'm going to show you the paths that each one of these will take in a bit. There's one more style where you kick in sort of a depressed manner. So you're going below the horizontal. And so this is called a depressed launch. Okay, so the vertical launch is going to look like this. So the ball is going to go up and then land down. The horizontal launch is going to look, it's going to go straight and then down. And then the depressed is going to look like that. Okay, so 3 different types of launches. So you have to read the question and sort of gauge what kind of launch it is. Okay. Now, I remember we talked about taking any motion in 2D and then finding out its components, meaning finding out its X and Y parts. Well, you have to do the same thing for projectile motion as well, because it is really motion in 2 dimensions, because it's moving horizontally and it is moving vertically. Mind you, though, it's happening simultaneously. Okay, I don't want you to think that the horizontal and the vertical motion are happening discretely or one after the other. The ball doesn't travel like this. Look, this is what does not happen. Okay, let's say you kick the ball from the ground level in that direction. Okay, the ball does not do this. It's not going to say, okay, I'm going to travel horizontally, then vertically, then horizontal, then vertical, one at a time. This is not what the ball is doing. That would look weird. Have you ever seen a ball being kicked and then the ball traveling like that and then suddenly goes up, then suddenly goes right? No, it doesn't happen that way. That's going to look weird. Actually, what the ball does is it's going to go up smoothly like that and then come back down. So when it follows the yellow path, which is what it does, it is moving to the right and upwards simultaneously. And that's why it moves along that curve. Then again, from there, it moves right and up together simultaneously. That's why it moves up. And so it takes the yellow path. Okay. However, it is still motion in 2 dimensions. And so you have to tease the entire problem apart into 2 parts, X and Y. And so what you do for every single projectile motion problem is you make a T-chart and you would write down everything you know about the X component and everything you know about the Y component. Okay. So let's say let's say you are actually kicking the ball. Okay, I'm just going to use one of the diagrams that I have. Let's just get rid of all of that because it doesn't move like that. Keep just the yellow part, okay? Even the yellow diagram, I don't like that much. I ended up actually drawing a new one anyways. Okay, so let's say you kick the ball in that direction. Let's say we knew the initial speed at which it was kicked. Let's say it was 18 meters per second. And we also know the theta was, let's say, 30 degrees, the angle that it made with the horizontal. Okay. Now, let's write down the stuff that we already know about the x and the y-axis. And remember, projectile motion, we're always going to neglect air resistance, no air resistance. Okay. What that means is, excuse me, it's horizontal motion will have constant velocity. V along the horizontal is going to be constant because we are assuming there is no wind. If there was wind, then the wind, whatever the direction of the wind is in that particular day, would impact the horizontal motion of the ball. But we are neglecting air resistance, which means if you give it a push of, let's say, 15 meters per second horizontally, that 15 meters per second along the x will continue to be 15. It doesn't change. And that's always going to be true. Speed along the x is going to be constant. Why? Because we are saying no air resistance. What that means is if V is constant, V along x is constant, obviously what that means is there is no acceleration along the x. Would you agree with that, folks?
Yeah.
Right? Because only if acceleration is 0, the object could be going at constant speed, right? So now, coming back to x in a little while, let's just jump over to the y side. Okay, now for the y side, we said that there is going to be a net unbalanced force of Fg. This force is not balanced. So this does become our net force. And when the net force is not 0, what's the object going to do? Remember last session, there were two options: when the net force is 0 and when the net force is not 0. We said when the net force is 0, the object may be at rest, or the object may be at constant speed, kind of like the x part of the motion. But what did we say will happen when F net is not 0? Anybody remember?
It will move.
It will move for sure, yes, but can you give me a little bit more specifics than that? This is what we did last session. What does it say? When F net is not 0,
it accelerates.
It accelerates. Wonderful, right? It is definitely moving, but moves as it accelerates. And so the acceleration along the y direction is definitely not 0. However, how much is it from kinematics? What's the vertical acceleration when you throw a ball upwards? What's the acceleration? If the only force acting on it is force due to gravity. Come on, guys, you should know
negative
this.
9.8.
You got that. It's negative 9.8 meters per second squared. And so the acceleration along y is that same negative 9.8 meters per second squared. Okay, so you want to treat this whole problem as though it's made up of two parts: x part, where it is constant velocity, y part, where the acceleration is negative 9.8. So for all projectile motion problems, folks, these two values will always be the same. Ax will always be 0, ay will always be negative 9.8. Okay. Now coming back to X, we are trying to populate this T-chart with more and more information. We know the VI value, 18 meters per second. Can I not determine its X component? Now we just did this in a previous question. Take a look at this diagram and tell me if you have enough information to determine the X component of VI. Do you have enough info, yes or no?
Info for what?
Info to find out VIX. So if you have this vector pointing in that direction, this vector is going to have two components to it. One along the horizontal, that's the VIX. And then you would have one along the vertical, that is VIY. Do we have enough information to find out VIX? I know the angle, I know the hypotenuse.
Yeah.
Okay, how would you do that? We did it many times further on.
VIX is the adjacent one.
Yes.
To 30 degrees. So you can do cos with the hypotenuse times cos of 30 degrees.
Beautiful. So you do 18 cos of 30 degrees, and this is going to be 18 sine of 30 degrees because that's the opposite. So hey, we already know the initial velocities along x and y. So 18 cos 30, that is 15.588, 15.5884 meters per second, and it is pointing to the right, is it not? Look at the green arrow, it's pointing to the right. The black arrow is pointing to up. So both those are going to be positive values, okay? So similarly, we can find out VIY, and that is going to be 18 sine 30 degrees. And so that is a flat 9 meters per second. Okay. Now, one last thing I want to make a note of is the time. The time for the X and the Y parts of the motion is going to be the same. Okay. The time in which, remember that the X and the Y motions happen simultaneously. They start together, the X and the Y part, and they end together. So the time in which the object moves from A to B horizontally is the time in which it goes up and comes back down. Both those times are equal. And so we cannot say Tx and Ty. Besides, time is a scalar value. So it doesn't have components. So time is equal for both X and Y, okay? So we're going to stop right here. We're going to continue from this point onwards next time we meet. For those of you who haven't taken a picture of the homework from the textbook, please go ahead, take that before we end the session. All right, ladies, have a good, oh, it's probably not night for you, but it's night for us over here. But have a great evening, guys, and bye-bye until we meet up next time, okay? Bye. Take care, folks. Okay, bye, Fiona. I don't know if you're able to hear me or not. Have a good night.